5 minutes. That's how long it took Google's new quantum computer to solve a calculation that would take the world's fastest classical supercomputer 10 septillion years. In December 2024, Google announced the Willow chip, and the scientist leading the project, Hartmut Neven, made a claim that dominated headlines. He suggested the chip's performance lends credence to the idea that it is computing across parallel universes. This raises an immediate question. Are we actually witnessing a machine that taps into alternate realities, or is the underlying verifiable physics far more important than the viral marketing? Regardless of the multiverse theory, the gap between 5 minutes and 10 septillion years suggests that classical supercomputers can no longer keep pace with quantum developments. To understand why, you have to look at how these machines process data. Your laptop uses classical bits, flipping switches between a strict 0 or 1. A quantum computer uses qubits, which operate more like a dimmer switch, holding both states at the exact same time through a property called superposition. Imagine solving a massive maze. A classical computer hits a dead end, backs up, and tries the next path. By using superposition, a quantum computer floods the entire maze, exploring millions of possible routes simultaneously to find the exit. The bottleneck has always been decoherence. Qubits are incredibly fragile. A tiny temperature shift, a stray cosmic ray, or minor vibrations in the room will destroy the quantum state and ruin the calculation. For decades, scientists tried to shield against this noise by grouping multiple physical qubits together into one stable system. But they faced a frustrating mathematical paradox. Adding more qubits to fix the system only generated more errors. Building a quantum computer was like trying to stack a massive house of cards in the middle of a hurricane. Every piece you added made the structure more prone to collapse. That scaling problem made commercially viable quantum machines seem decades away, until Google's recent test. Google changed their strategy. Instead of packing thousands of physical qubits onto the Willow chip, they prioritized stability, chasing quality over raw quantity. Engineers arranged 105 physical qubits into highly precise grids. They started with a tight 3x3 layout, expanded to 5x5, and finally pushed to a 7x7 grid. This graph shows system noise relative to qubit count. As Google expanded the grid, the error rate plunged downward exponentially. This is below threshold error correction. At the 7x7 grid, the quantum state lives twice as long as an isolated qubit. Google has reached a tipping point in hardware design. Willow is the first system to demonstrate that a larger grid can actually protect quantum information longer than an individual qubit. The 10 septillion year calculation makes for a great headline, but critics correctly point out that it is a highly theoretical benchmark engineered entirely to make classical computers fail. So Google ran a second, verifiable test called quantum echoes. This measures chaotic noise inside quantum systems, a calculation directly applicable to mapping complex molecular structures for pharmaceutical drug discovery. A classical supercomputer would require 150 years of continuous processing to verify this molecular interference. Willow completed the exact task in just 2 hours. By delivering a 13,000 times speedup on a problem with actual scientific value, quantum computing officially transitions from a theoretical physics experiment into a reproducible engineering tool. The immediate question is whether this raw computing power threatens global finance. Right now, the answer is no. Willow operates at 105 physical qubits, and breaking the encryption securing Bitcoin requires roughly 500,000 perfectly stable qubits. However, research released by Google in 2026 revealed that defeating cryptocurrency encryption requires 20 times fewer resources than security analysts previously modeled. Experts track this through a concept called Q-Day. That is the rapidly approaching deadline when quantum machines will possess enough stable qubits to shatter current global encryption standards. The danger is not entirely in the future. Hacker collectives and nation-states are executing a strategy known as harvest now, decrypt later. They are aggressively stealing and hoarding encrypted bank records and government communications today, waiting for the hardware to catch up. Institutions are preparing. The U.S. government finalized 3 post-quantum cryptography standards, mandating that federal agencies fully migrate to quantum-resistant encryption by 2035. Because hostile actors are already hoarding massive troves of sensitive data on their own servers, the security vulnerability is a present reality, not a future hypothetical. Google is running a multi-billion-dollar race. IBM is pushing for massive raw qubit scale. Microsoft is betting on inherently stable topological hardware designs. And China has poured $15 billion into state-sponsored infrastructure and satellite communications. Which brings us back to the viral claim about parallel universes. While the quote generated massive media coverage, theoretical physicists across the industry have roundly debunked it. The scientist was referencing the many worlds interpretation. This is a philosophical framework some physicists use to conceptualize how quantum mechanics operate. It is not a literal, mathematically proven requirement that alternate realities exist. The actual value of this technology lies in practical, earthly applications. The market is projected to reach $20 billion by 2030 because these machines will drastically reduce the energy required to train AI models and simulate chemical bonds for ultra-fast pharmaceutical development. Willow likely didn't prove the existence of parallel universes, but by demonstrating below-threshold error correction, it turned a decades-long scientific hurdle into a 5-year engineering race toward a million-qubit processor.